introduction on the fundamentals of machine learning. And so for those who may have seen the educational series last year, 2024, this particular talk will be an abridged version of that. And so first, let's start with what is machine learning and why might we be interested in using it for astrobiology. So machine learning is about designing algorithms that automatically extract valuable information from data. And machine learning is inherently data-driven. However, with growing complexity of data, there's currently a paradigm shift towards knowledge-informed machine learning. And that's kind of where astrobiology comes in. Because astrobiology has a lot of complex data, especially in modern times, also very large, such a way that it's really difficult for humans to extract important information, at least in an efficient way. And artificial intelligence, you'll often hear this. I mean, even I guess for this website, artificial intelligence, machine learning is very broad. But really, it's this interdisciplinary field, as we kind of see with the attendees today, that includes fields such as mathematics, statistics, information theory, game theory, optimization, and a few others as well. But artificial intelligence really is just a broad umbrella term that encompasses many different branches, such as machine learning, robotics, as we heard earlier, planning, natural language processing, and a variety of other things. And then within machine learning, we have a few other smaller branches, such as supervised machine learning, unsupervised learning, semi-supervised, reinforcement, and deep learning. And really, for the purpose of this crash course or this introduction, we'll focus on the machine learning branch, as this is what is really valuable for a lot of astrobiological research, but we'll hear later today that obviously robotics is going to be very important as well. And so of these branches, supervised learning, unsupervised learning, and deep learning are really our prime components that I'll focus on for the rest of this talk. And so I'll first start with unsupervised learning. So what is that and what does that really mean? So IBM has a great quote that describes unsupervised learning as essentially a process to analyze and cluster unlabeled data sets. More specifically, these particular algorithms are able to discover hidden patterns or data groupings without the need for human intervention. And there are many different use cases for unsupervised learning, including dimensionality reduction, clustering, and anomaly detection. And I'll describe a little bit of that in this talk. So first, let's start with the first use case, dimensionality reduction. So one of the prime uses for unsupervised learning. So dimensionality reduction is really a method to represent data, high dimensional data, in a lower dimensional space, while still capturing the original data in this higher dimensional form in a meaningful property. And so that's kind of an esoteric explanation and can be a bit challenging to visualize. However, we can do it. So dimensionality reduction, we can think of as perhaps looking at this left side, taking a cube or some prism and reducing it to a square, its two-dimensional form, and then perhaps a line in one-dimensional form. In this way, we can see that the original data, or this cube, these prisms, we're able to capture the global properties of these high-dimensional forms. In a way, we can do that with data as well, specifically data sets that we obtain from astrobiology. And so you'll often hear of different algorithms like standard PCA or principal component analysis. And I won't describe these in too much detail since we'll hear a little bit more about some of the algorithms that people will discuss later in this workshop as well as in person. But standard PCA is similar to what I just described here, where we can take high dimensional data and reduce it to something that is in a low dimensional space. And here we can see these groupings of these different colors in three-dimensional space, and the same patterns are remain in the two-dimensional and a little bit in the one-dimensional space. So this really allows us to understand these really complex data. And here I'm just showing how this particular algorithm works, but it essentially finds the linear transformations of these data. So it's really great algorithm to use if you have data that is not extremely complex and perhaps assumes some linearity. However, we know with astrobiology that's often not the case, earth sciences as well, where we often have non-linear types of data, whether it's non-linearly separable or non-linear relationships. And so if we want to better identify patterns in the high-dimensional space with these more complex data sets, we can use algorithms such as t-distributed stochastic neighbor embedding, which really allows us to understand what the data looks like from a nonlinear perspective. And because of the complexity of this algorithm, there's actually a lot of fine tuning or hyperparameter tuning involved in which we can look at different aspects of the data. It's important to note that this is not the only type of dimensionality reduction that can be used. There are many different algorithms, but these are just two prime examples. There's also clustering, so the second use case for unsupervised learning, which is essentially a way for us to classify different objects or data into groups of clusters, again, without human intervention. And so here I'm just showing the variety of different clustering methods. Well, I'll only focus on a few here, but there's many, many different algorithms that you can use to understand groupings within data sets. But one of the primary ones is k-means clustering. So very similar to the use case for principal component analysis. And what I mean by that is it's a relatively simple algorithm that is great for data that is a bit more simple in terms of its structure. So here we can see these spherical or globular structures within the data. And the way that k-means works is it identifies centroids within those data clusterings to essentially create a classification. So this works really nicely if you have data that can be separated into groupings such as this. However, much like the dimensionality reduction, and very often the case with astrobiological data, is we're often working with data that is not linear and perhaps has even more crazy structures within the data. And so dbScan is another type of clustering algorithm that can be used to understand the structure of nonlinear types of data. And so here's a really nice GIF showing how this works. And I can discuss more how this algorithm works for people who have questions, but this is really just a very brief explanation. But unlike the k-means, which requires these spherical clusters, dbScan can actually identify things that are not necessarily spherical, such as this particular cluster here, and then the spherical clusters within this circle. And so we often do see data like this in astrobiology. Perhaps maybe not a smiley face such as this, but maybe something similar. Then we also have autoencoders, which are a type of unsupervised learning that's often used when we're thinking about neural networks. And essentially the way they work is they provide a compressed version of the input data that you use for neural networks. And I will describe neural networks a bit later here. And more specifically, it's a lower dimensional representation of that. And so here's just kind of a brief example of what an autoencoder might look like. And so let's say we have input data of images of animals such as cats or dogs. The way that an autoencoder works is it encodes the data, so your image data, and then it sends it into a latent representation or a low dimensional representation. So perhaps we identify patterns such as ears, whiskers, snouts, etc. And then we can decode that data and make some inference about what we see from this image classification. And so autoencoders are really great if you're working with neural networks. Okay, so I talked a bit about unsupervised learning, but supervised learning is also very valuable for applying machine learning to astrobiology. And more specifically, supervised learning is defined as the use of labeled data sets. So in this case, there is some human intervention to train algorithms to classify data or predict outcomes from data. And so there are many different use cases for supervised learning, such as classification and regression. And if you want to learn a little bit more about it, there's a really great paper from 2023 by Dupont and others who describe the use cases of unsupervised and supervised learning for their data, specifically for mass spectrometry. Supervised learning, as I described in the previous slide, is divided into two main classes. So one being the traditional machine learning approach, which incorporates classification and regression. Then you also have deep learning, which also is classification and regression. But again, deep learning is a bit different. But how different? With classical machine learning, there is an added step, more specifically a feature extraction step. So there's a lot more human engineering involved with classification or classic machine learning. But once we extract these features, we can then train a classifier and get an output. Deep learning works a little bit more differently in that it's complex and it can extract features on its own. So even without human intervention. So you do have the labeled data sets that are a component of the supervised learning, but it is able to extract those features without the use of human intervention. And so again, the classic machine learning does require feature engineering. So you often hear the term feature engineering, whereas deep learning does not necessarily require that. So obviously there's similarities between traditional machine learning and deep learning. So which one to choose? Well, there are different instances, and I'll just kind of skim through this a bit, but there are different instances in which we might want to use traditional versus deep learning or neural networks. And so oftentimes maybe we're working with small data sets that are quite complex or has a lot of variables. Well, traditional machine learning approaches are actually going to perform a little bit better because neural networks or deep learning require a little bit more data to actually learn those features. So since they are doing the feature extraction inherently, they do need a little bit more data. And so if we're working with a lot of data, then perhaps deep learning, deep neural networks specifically, are going to be what we want to choose. And so depending on what your actual data sets look like, you can choose between traditional machine learning, shallow neural networks, or medium neural networks, and deep learning. And it's important to note that as we go up the y-axis, the computational performance or computational cost does become more expensive. So that's something to keep in mind. And so I'd mentioned that there are two classes for supervised learning, one being regression and one being classification. And with regression, essentially we're using supervised machine learning to understand and predict continuous outcomes, whereas classification we're using to predict different groupings of data. So in this case, circles versus squares, or perhaps high abundance of organic carbon versus low abundance of organic carbon. Most algorithms actually can perform both regression and classification, with some exceptions, of course. And so I'll describe a bit of the traditional approaches on the deep learning. But logistic regression is an algorithm that can be used for supervised machine learning, in which it essentially converts predicted values into probabilities and uses a sigmoid curve to classify that. This is really great for linear data, linear separable data. K-nearest neighbor is another algorithm that is really great that for more simple structures of data. And essentially the way this works is it chooses a predefined K, which is the number of neighbors, hence the name K-nearest neighbors, and uses the data to understand where it should classify the point. Then we also have support vector machine, which is a different type of algorithm that is a little bit more complex and perhaps a little bit more black box than the logistic regression and K-nearest neighbor, but it's really effective with handling nonlinear types of data frames. And same can be said for the random forest. And again, I won't describe too much how these algorithms work, but these particular algorithms are really great for nonlinear data. Deep learning, on the other hand, is a method that uses very similar approach to how we might think of the human brain, hence the name neural network. So it does resemble the structure of the neuron cell in the human body. So basically taking inputs and activating things, and we're able to get outputs. The most common type of neural network that many of us are probably familiar with is the artificial neural network. This actually is not an artificial neural network technically, but anyways, we have some input layer, a hidden layer, and an output layer. And so this input layer is some representation of our data. The hidden layer is where the decisions are happening, and then the output layer is the classification of that your input data. So this is really great for if you're working with, say, spreadsheets, but really large number of data points. Convolutional neural networks are another type of neural network that are really great for image classification because of the way that they work. They're able to identify patterns and features within image data sets. And then we also have recurrent neural networks, which is going to be your type of neural network that would be used for forecasting data, maybe even backcasting data. And so we can see that there are different approaches and methods that you can use for neural networks. There are many different toolboxes too. I won't describe these in detail, but you can do a lot of this programming in Python, such as using TensorFlow, scikit-learn, and also R using tidy models. And many applications of machine learning currently for works that has been presented in the last couple of years have been really based on like agnostic biosignatures, biosignature detection, mass spectrometry. And you can see a couple of examples here in these papers. But that's where a lot of this future directions for the application of machine learning and astrobiology are. And again, we'll definitely hear a lot more about that throughout this workshop. And yeah, that's it. So it's a very brief crash course on machine learning fundamentals, but definitely check out the other resources from the website that Ryan has. And also JGR has a great new journal for machine learning and computation.